Hi there, folks. Today we're looking at modeling relationships and really, in a more specific sense, we're modeling relationships that either model linear, quadratic, or exponential functions. This is kind of a continuation of that study, but now we're looking at it in terms of the situation. So previously we looked at, is it linear, quadratic, or exponential based on the equation, based on the graph, based on the pattern of the values, so based on the table. Now we're looking at it based on the situation. For example, this first one says the water from one water cannon on a firefighting boat reaches a maximum height of 25 feet and travels a horizontal distance of about 140 feet. What type of function best represents the situation? So again, if you're kind of thinking about this thing off to the side here, if we kind of think about a boat, so we've got a boat here. I don't know why the firefighter boat is a sailboat, probably because of budget cuts or something like that. But they're trying to put out a fire from the water. So here's the fire. And what happens is if the cannon shoots water, it's going to travel up into the air, but because of gravity, it's going to come back down eventually, all right? And it's going to land somewhere. And if you've ever used like a hose or something like that, you know that that's kind of how it works. Because of gravity, it arcs through the air like this. And so just thinking about the situation, that's clearly a quadratic equation, and I'm just going to abbreviate a little bit there. So it's quadratic because of gravity, and we've kind of talked about that a little bit. And now it asks me to sketch a graph. Here's the thing, this graph is not going to be 100% accurate. We're just going to do our best to kind of get a handle on the situation. And I'm going to graph it for the most part from the positive perspective. So like here's my X and Y axes. Notice I cut the negatives off for the most part. And when you think about this, think about like where the values start here. It's going to start up in the air somewhere because the cannon is on the boat. It's not at ground level. It's going to arc through the air and then come back down. Okay. And it's not going to continue to go back down once it hits that ground level. That's it. I mean, I guess it could seep into the ground or whatever, but we're going to kind of cut it off there in terms of the height. And so it gives me some information here. It says the maximum height is 25 feet, so it's describing the y value at this point right here at the very tippy top of this thing. And then it says that it travels a horizontal distance of 140 feet. So you know that this is 140 right here, so that would be the ordered pair 140 comma 0. And when we look at kind of this guy, this one over here is kind of an unknown because we don't know at what height this thing is starting at unless you have in-depth knowledge of what one of these boats would look like. That cannon is up in the air somewhere. We just know it's not at 0, okay? We know it's above ground level or above sea level, I guess in this case, all right? And then the last piece of this thing is this guy is kind of an unknown but kind of a known, this y value right here for the vertex. We know it in a sense that it's somewhere around the halfway point, and from here to here is 140, so that's somewhere around 70. But can we make the assumption that it has to be a little bit less than 70? See, here's the thing, that's in the middle if this parabola were to continue, all right, which means from here on over is 70, and then from here to this end is also 70. So this one actually comes up a little short. So maybe I'd say it's something like, I don't know, 67 if I was estimating, kind of taking a guess at it. Okay. Now again, that value is not exact. Maybe I'll put a little asterisk next to that one. But we're kind of just getting a sense of what this thing is supposed to be like. It should be a little bit less than 70. And again, that would be determined. We'd be able to figure that out exactly if we knew this height right here. Okay. So there's my quick sketch, just giving me an idea, a sense of the situation. And then down here it says, what do the intercepts and maximum represent on the graph? So we have a couple different versions of the intercepts. We have the y-intercept. Let's start with that one. The y-intercept is kind of like where this function starts. The y-intercept is essentially the height of the water cannon. And again, that's where this thing starts. And then we have the x-intercepts. Really, for our purposes, it looks like on the graph, because I extended a little bit, that there are two x-intercepts. But really, there's only one, because the other one is in the negative region of this thing. But the x-intercept would be at ground level. It's where the water hits the ground. Okay. And then the maximum, remember the maximum is also the vertex, so we can call it the vertex as well. But that just represents the highest point of the water here, and we know that that's the somewhere around 25 feet, I guess it was. I don't remember what the units were. Yeah, feet. So the biggest part of the height. So I know my letters. B is the one that has two of those little bubbles on it. Yeah. So again, we're just kind of interpreting what each of these things represents. Again, that was at 25 feet. And it happens somewhere around a horizontal distance that's a little less than 70. Okay, but again, we're just describing the situation. And if we had more information, we could come up with an equation of this thing, and then we could interpret piece of that equation, and we could solve for different pieces of that equation, and all kinds of stuff. But we're just using the information we have to kind of interpret what the situation is. But look at the next one. It says the table shows the revenue generated by a company over a 5-year period, and we want to know what kind of function is. So we're looking for a pattern, and maybe you would look at this and say, okay, to get from 50,000 to 51,500, you got to add 1,500. And then to get to the next one, I add 1,545. So it's not linear. I could check to the common difference, but spoiler alert, that's not going to work either. The solution for this one is it's actually exponential. And here's a good way to figure that out. So I pulled up my calculator here. If you're not sure, like, how do I get from, 50,000 to 51,500 by multiplication, just work backwards. Take the 51,500 and divide it by 50,000. So it gives me a 1.03. And now I could check that. I could take the 51,500 times the 1.03 and see if it gives me the next value, and it does. I could scoot this guy out of the way, and I could multiply that by the 1.03 and see if it gives me the next value, and it does. And then, well, approximately, it's rounded off. And then that times the 1.03, and that gives me the next value, okay? Again, these are rounded off, but that's the pattern here. I'm multiplying by 1.03 each time. So the best representation, even though it's rounded off and I cut off the decimals, that's okay because it didn't ask for the exact representation. And maybe this is exact, but they just don't have that on the table. The table's rounded, okay? But it asked for the closest. It asked for the best representation, okay? And the best representation here, it models pretty closely to multiplying by 1.03, okay? So it's an exponential function. And now it wants me to predict the revenue in 2018. See, this one is one where we kind of have to interpret this thing and write an equation. All right. See, the last one we were just interpreting and kind of figuring out the situation. But now this one, we need an equation in order to make predictions. So here's what I'm going to do. I'm going to call this year 0, year 1, 2, 3, 4. And I did that because that makes it really easy to write an equation because remember, it's y equals a times b to the x, where a is the y-intercept. Well, now the y-intercept is 50,000. See, because I referred to that as year 0, that was the starting value. The thing I'm multiplying is the 1.03. And now I just have to figure out what 2018 is represented by. So if year 0, if 2008 is year 0, 2009 is year 1, 2010 is year 2, keep counting, what would 2018 be? And so if you count this out correctly, oh, sorry, I shouldn't write it over here. The year 2018 seems to be, I believe, year 10. So all that's telling me to do is, hey, plug a 10 into this thing. All right. And now it's a job for my calculator. So let me pull my calculator back up. And so here we go. I do 50,000. Whoops. times 1.03 raised to the 10th power. So it's giving me 67,195 and 81 cents. I'm going to round to the nearest value because that's what it's done in the table. All right. Normally I would round to 2 decimal places because we're talking about money, but this time I'm going to round to 67,196. Because that's the way it's estimated in the table, that's the way I'm going to estimate it here. Okay. But again, we interpreted this thing. We found out that it was following an exponential model. Then we used an equation to make a prediction about that model. But like this one, a furniture salesperson earns $200 per week plus a 5% commission on the total value of all sales. What type of function best represents the situation? And see, this one's a little bit tricky. As soon as we see a percentage, we start to think exponential, but this one is a mislead. And so when we think about what's happening here, this one's easiest if you kind of think about the equation first. So if you think about the situation, say, you know what? He starts with $200 no matter what, but then to that, he's going to add 5% of whatever he sells. So 0.05 times however much money he makes. And see, now when I look at that, hopefully you can see that that's really y equals mx plus b. Yeah, it's a little mixed up. It should be 0.05x plus 200, but that is a linear type of equation, all right? We're starting with a set amount, and we're adding a set amount based on how much he sells, okay? So it's a kind of multiplication. It's multiplying by how much he sells. That's describing y equals mx plus b. And so again, as we sketch a graph of this thing, not anything real intense here. Notice I'm cutting off the negatives because we don't really need those. But he starts up here at 200. And then if he sells $100 worth of stuff, he earns an extra $5. And if he sells another $100 worth of stuff, he'll earn another $5 and another and another. And so that thing will continue to climb, okay? And so it follows the kind of this linear model. And really what it's showing us is what his income is going to be based on how much he sells, okay? And that's what follows a linear model, all right? Down here it says 2 linear functions are described below, and we just want to answer a question about them. So it says which line is increasing at a greater rate? And so when you think about the rate of increase, the rate of change for a linear function, we're talking about slope. Again, that's rate of change. So this one, I would kind of think of it this way. The x-intercept is 4, so that's the order pair 0, 4. 4, 0. The y-intercept is -2, so that's the order pair 0, -2. And then from here, you could do your slope formula. You could do change y over change in x. Heck, you could graph those and just do counting to get from one to the next. All right. So I'm just going to do the change y over change in x. The y went down 2, and the x went down 4. So that's a 1/2. So that's my slope. And then this one, when I'm looking at a table, I just look at change y over change in x from a different perspective. Like here, it's going up 1 each time. So that's the change in x. Here it's going up 5 each time. So that's the change in y. So if I do change in y over change in x, that's 5 over 1, which is 5. And so when I want to know which one is increasing more rapidly, well, it's obviously the 5. All right, because 5 is bigger than 1/2. So it's the linear equation B. And in this last one, now we're comparing 2 quadratic functions. And we want to know which quadratic has the lesser minimum. And so when we look at this guy, we can see the minimum value right here. It looks like something around, and again, we have to estimate because of where it is. Looks like a -2.5, and then maybe something like maybe a -4.5. So when we're talking about the minimum value, remember we're talking about the y value. So this one has a minimum of -4.5. To find the minimum of the other one, remember the minimum is the same thing as the vertex. Maximum is also the same thing as the vertex. So to find it when it's in standard form, remember I have to do the opposite of b over 2a. So the opposite of b is a 12. 2 times a, which is a 3. So that's 12 over 6, which is a 2. Now that's just the x value, which is not what I'm looking for here. I'm looking for the y value. So I have to plug that back in. So I'm going to plug that guy in for x. And again, just be careful here. Follow order of operations. That's 3 times 4 minus 24 plus 1. So let's see, that's a 12 minus 24 plus 1. So that's a negative 12 plus 1, which is a negative 11. And so when I compare the two, it looks like the first quadratic drops lower than the second quadratic because it drops all the way to a negative 11, whereas the second one only drops to a negative 4.5. So the answer here is letter A. But again, it's just about kind of looking at the situation and saying, okay, what kind of function am I dealing with? How do these functions act? And how do I find these different pieces so that I can compare and contrast these different things and model them to some situations? Okay?